In this video, we present our work generating upper body motion for real-time characters making their way through dynamic environments. Animating responsive characters in complex environments is of utmost importance for video games and virtual reality. Dynamic scenes, including plants or buses, are a particularly challenging example when we address the problem of generating reactive, lifelike motion based on our internal state and the surroundings. In this work, we propose a hybrid method to create upper body motion interactions based on the character surroundings. Our method combines keyframe inputs, kinematic constraints, and lightweight physics to leverage antagonistic controllers and create a responsive skeleton, allowing us to modify the amount of tension and relaxation without diverging from the reference motion, while an anticipation model and a set of procedural rules enable high-level authoring to define the behavior. Our hybrid approach couples keyframe animation and lightweight physics for human-like characters. The way we do this is by switching between physical and kinematic spaces for different body parts independently, like for the arms or the head, allowing the game designer to improve the interactive motion of predefined kinematic controllers based on the effects that the dynamic environment might have upon the character. This method can adapt automatically to generate the appropriate dynamic response, for example, by transferring a limb exposed to a hit from kinematic to physical space. For a given hybrid skeletal configuration, we leverage antagonistic controllers for the responsive skeleton to follow the reference kinematic motion. As we can see in our demonstration, such controlling strategy allows us to decouple position and stiffness control for each degree of freedom. This enables to actuate a joint and change the amount of tension or relaxation without diverging from the target orientation. We use antagonistic controllers to actuate the responsive skeleton for our character, by introducing actuator torques for the joints in the physical space to imitate the kinematic motion. We can combine this method with inverse kinematics to generate plausible responsive variations of our reference motion against external phenomena. High-level authoring can also be achieved thanks to a linear representation for the joint position and tension, so the user can navigate interactively through different stiffness configurations. To improve automation when tuning our responsive skeleton in complex environments, we provide a high-level yet customizable anticipation and action method. A frustum-like visibility region is used as a means to make the character aware of the environment and any external obstacle. A set of safety regions on different limbs represent body parts that the character might want to protect when working on dynamic scenes. The metadata retrieved from the environment, along with a set of high-level procedural rules, are used to interact with the surroundings by modifying the kinematic reference animation and therefore actuating our responsive skeleton against any objects coming inside the safety regions. The set of rules remains flexible, yet general enough to deal with different types of behavior, for example by updating in discrete steps our hand position with the object or sliding the hand while we are in contact. The combination of the actuated responsive skeleton with the stiffness-based controlling strategy and our anticipation system defined by procedural rules allow us to generate plausible upper body animations, for example in rich, highly diverse natural environments. In this example, we can see how different amounts of tension affect the interactions of the character with external objects of different mass. As we deal with heavier obstacles, a stiffer configuration of the pose is beneficial to handle the interaction, while weaker variations find more trouble to push objects with more mass. Another aspect that might be changed by the user is the reaction time required by the character to reach the obstacle. Slower movements precipitate situations in which the character is caught off guard, so that contact with the object is not fully established. In our experiment, we have created a rich 3D environment where the character can properly anticipate the nature of the obstacles and react against them. In this example, we saw how the character adapts the stiffness using the anticipation model to retrieve the expected mass of the external natural objects found in the way. This adaptation might lead to a better resolution during interactions, for example by reacting more relaxed against elements that might not require much force to be pushed apart, like high grass or flowers, or having a more tense pose when we are pushing heavier obstacles, like the fence door. Thank you.